Nature of energy, key definitions. This section will all be on our introductory definitions. All of the definitions that we're going to cover in this video are going to be expanded and used later in the chapter. This is just going to be a taste of each of the concepts that we can then expand. So what are we going to cover? First, we're going to start out by defining thermodynamics, energy, work, and heat. And then we're going to talk about the different types of energy, so potential versus kinetic, and thermal and chemical. Those are going to be our main ones. We'll kind of mention the other ones, but mostly we'll focus on thermal and chemical energy. And then lastly, we just need to talk about two definitions that will help us discuss everything else in the chapter, which is define our systems versus our surroundings. And finally, we'll define state function and extensive properties, which again are just helpful for us to talk about the different properties that we'll be discussing throughout the chapter. So first off, this is our first chapter on thermodynamics, so we should talk about what thermodynamics is. Thermodynamics is our general study of energy and its interconversions. We will cover this in this chapter, again in several sections of later chapters, and then finally another full chapter near the end of the class. Here we're going to be focusing on enthalpy, and we'll use this in a variety of applications throughout the coming chapters. When we have our second full chapter on thermodynamics, we're going to be covering entropy and Gibbs free energy to complete our discussion. Energy is our capacity to do work. This is a quantitative amount that is possessed by an object or a series of objects. It can be transferred between objects or transformed into different types of energies. We'll talk about this transferring on the next slide. We have two ways of exchanging energy. We have heat and we have work. These are the only two ways that it can be transferred. Although there are several subtypes of each, these are sort of the umbrella ways of talking about it. Work is when a force acts on an object, or when an object exerts a force on something else. The force times the distance is the work. So think about somebody lifting a weight. The force that she exerts on the weight over the distance is the work that she does. Heat is the transfer of energy, and this is caused by a difference in temperature. Heat flows from high energy, or high temperature, to low energy, or low temperature. Both of these are going to be covered in far more detail in later videos, and will have their own video as well. Kinetic energy is the energy of motion. Anything that has a velocity and mass also has kinetic energy. One specific type of kinetic energy that is important in chemistry is thermal energy. This is the energy that is associated with temperature. Hot molecules move faster is an example of a concept that thermal energy gives us. We'll discuss thermal energy more later as well. Potential energy is the energy that is stored in an object, or an energy that is associated with the composition or position of an object. There are many, many types of potential energy. We're actually going to start with one that doesn't have a lot to do with chemistry, because perhaps the easiest to understand is gravitational potential energy. If an object, or person like this climber, is very high above the ground, then he has lots of potential energy. As he falls, he loses potential energy and would gain kinetic energy as he speeds toward the ground. The most commonly discussed potential energy in chemistry is chemical potential energy. This is the energy that is stored in a compound due to its chemical composition of its bond. We'll discuss this energy more later, but it helps us run things like batteries and lets fireworks happen, along with many, many, many other things. Now we have to quickly review units, and I thought that this fit well in the definition section. So first off, what is our SI unit of energy? I know that we've talked about this before, but it's good to review it. Our SI energy unit is joules. And remember that a joule is 1 kilogram meters squared over seconds squared. So sometimes it's useful to break that up. We'll also use calories. And we know our conversion for this is 1 calorie is equal to 4.184 joules. Now I want to remind you of something that you may have forgotten, but is very important. And that's little c calories versus big C calories. And this can get especially confusing because of capitalization at the start of sentences. But when you write the unit, if you write the unit with a little c, that is referring to the 4.184 joules calorie. But there's also something called a kilocalorie, and this is what we would think of as dietary calories with a capital C. So 1 capital C calorie is equal to 1,000 little c calories. Now let's talk about systems versus surroundings. These are two terms that we are going to be using constantly in this and later chapters. We define the system as the area that we are looking at, or the area under investigation. The surroundings are literally everything else. Technically, we define that as everything that the system can exchange energy with. But really, you want to think of it as everything other than that one area that you are investigating. The systems and the surroundings together make the universe. Now, this may seem like a silly set of definitions, but we discuss things in terms of systems versus surroundings very regularly. This is very arbitrary depending on our situation. We define what we want to investigate. And I do need to talk about convention. So convention here, whenever we talk about delta E, if we don't specifically specify what we are talking about, it is defaulted to talking about the system. So if we ask about delta E or later on Q or work or anything, we are actually asking about the system unless specified otherwise. Now let's talk about a state function. We'll talk about several different things throughout this chapter that are state functions. Right now we'll keep it simple. A state function is a function that depends only on the initial and final points, not the path. For example, if I walk up a mountain and my friend climbs a mountain and we started at the same point and ended at the same point, our elevation gain is the same. However, it may have taken me 30 miles and my friend 5 miles. The distance doesn't change how much elevation we gained. When things are state functions, it allows us to ignore the pathway. This is incredibly useful, and we'll use this a lot throughout these chapters. So some examples of state functions are temperature, pressure, concentration, and physical state. It doesn't matter if water has frozen and refrozen 5 times versus 3 times. All that matters is what state is it in now. It doesn't matter if the temperature change went up and down, just where the beginning is and where the end is. Remember that the change for these is always final minus initial. So our final value minus our initial value. Our last set of definitions for this chapter, or for this section, is extensive versus intensive property. Extensive properties are based on the amount of a substance. So, for example, mass is the obvious example. The more mass you have, the more of the sample you have. The same thing for volume. If you have more of the sample, you have a higher volume. If you have more of the sample, it might be longer. An intensive property is not based on the amount of a substance. So, for example, for temperature, it doesn't matter if you have a lot of a substance or a little bit of a substance. The temperature is going to be the same regardless. It doesn't matter if you have a lot of the substance or a little bit of the substance. The color is going to be the same regardless. So this extensive versus intensive property is a useful thing to be able to use while talking about different properties. Now let's review everything we've done. So we'll first off start with a review of just the energy, and then we'll cover all the other definitions. We had 2 main types of energy. We had kinetic and potential, and there are going to be lots of each subtype, some that I listed here that we didn't even talk about earlier, but we're going to be focusing on 2. We're going to be focusing on thermal and chemical. Later on in Chem 1, you'll also talk about electrical and nuclear. Now let's quickly review each of our definitions. Work and heat have their own videos, so I'm not actually going to review them here. We have our system, which is our defined area of investigation. We have our surroundings, which is everything else. Together, the systems and the surroundings make up the entire universe. We have our state function. Anything that's a state function only depends on the current state and not on the pathway that it took to get there. We have our extensive property based on the amount of a substance. So the more of a substance you have, the higher its mass. an intensive property, which is not based on the amount of the substance. So for example, if you have more of a substance, it's not going to change its color.